And the crazy part is, Netflix sees peaks of over 400 million requests per second hitting their APIs. Can you even imagine trying to handle that kind of load?
400 million? That's astronomical. What happens if they don't have proper rate limiting in place? Does the whole service just grind to a halt?
It's not just a slowdown, Shrija. It's a cascading failure waiting to happen. Imagine a sudden surge of requests, maybe a new season drops, or there's a global outage somewhere else that drives traffic their way. Without rate limiting, those APIs get overwhelmed. Databases buckle, services start timing out, and suddenly your users are staring at the dreaded spinning wheel of doom. It's not just embarrassing, it's lost revenue, frustrated customers, and a team scrambling to put out fires.
So it's about protecting the entire ecosystem, not just individual endpoints, because I can see how a single overloaded service could take down dependencies.
Exactly. Think of it like this. Your API is the city's water supply. Rate limiting is the dam that prevents a flood from washing everything away. You need to control the flow to ensure everyone gets their fair share and the system doesn't burst. We're talking about fairness, stability, and ultimately the survival of your service during peak demand. Imagine Uber during New Year's Eve. Surge pricing is a form of rate limiting in a sense, but they also need technical rate limiting to prevent malicious actors from hammering their systems looking for vulnerabilities during the chaos.
Okay, the dam analogy makes sense. So how do these dams actually work? What are the main approaches to distributed rate limiting?
There are a few key algorithms, each with its own strengths and weaknesses. Let's start with the simplest, the token bucket. Imagine you have a bucket that fills with tokens at a steady rate. Each request costs a token. If there's a token, the request goes through and a token is removed. If the bucket is empty, the request is dropped or delayed.
So it's a pretty straightforward way to meter traffic, right? What happens if there's a sudden burst of requests that exceeds the bucket's capacity?
That's where the burst size comes in. The bucket has a maximum capacity. You can handle short bursts of traffic above the refill rate, up to that capacity. It's like having a small reservoir behind the dam for unexpected surges. But once the bucket is full, any further requests are rejected. Netflix might use this for less critical APIs, where occasional throttling isn't a huge deal.
But wait, doesn't that mean you're just pushing the problem further down the line? If a user gets throttled, they might just retry, making the problem even worse.
That's a great point. The key is to return informative error messages to the client. Tell them why they're being throttled and when they can retry. Implement exponential backoff on the client side to avoid creating a retry storm. And of course, monitor those error rates like a hawk to detect potential issues.
Okay, that makes sense. Token bucket is the first approach. What's another common algorithm?
Another popular one is the leaky bucket. It's similar, but instead of refilling, the bucket leaks at a constant rate. Requests fill the bucket and they're processed as long as there's space. If the bucket is full, requests are dropped. The leaky bucket guarantees a consistent output rate, which is great for smoothing out traffic spikes.
So leaky bucket is better for ensuring a consistent flow, while token bucket allows for some burstiness. Where would you see this applied?
Exactly. Think of something like a video encoding pipeline. You want to ensure a steady stream of encoded video frames, regardless of the input rate. A leaky bucket would be perfect for that. Or consider Cloudflare protecting against DDoS attacks. They want to maintain a consistent processing rate, even when under attack.
Okay, I'm getting a feel for the differences, but both of these seem centralized. How do you scale these algorithms to handle Netflix-level traffic, which is distributed across many servers?
That's the million-dollar question. This is where things get interesting. You need to move from a single bucket to a distributed system of buckets. One approach is to use a shared cache, like Redis or Memcached, to store the token counts. Each API server checks the cache before processing a request.
But wouldn't that create a huge bottleneck on the cache server? Every single request has to go through it.
Nodding. Precisely. That's the challenge. You need to shard the cache intelligently. One way is to shard by user ID. All requests from a particular user always go to the same cache shard. This reduces contention and improves performance. Think about how Uber might shard their rate-limiting cache based on rider ID to prevent one user from overwhelming the system.
Okay, sharding helps, but what about consistency? If one server updates the cache, how do you ensure that other servers see the updated value immediately?
That's where you need to consider trade-offs. You can use strong consistency, but that comes at a performance cost. A more common approach is to use eventual consistency. Servers might see slightly stale data, but the system will eventually converge. This is often acceptable for rate limiting, where a few extra requests are less critical than overall performance.
So, eventual consistency is usually good enough in this case.
Correct. It's a pragmatic choice. Google, with their massive scale, almost certainly relies on eventual consistency for many of their rate-limiting systems. The key is to carefully tune the parameters and monitor the system to ensure that the eventual consistency doesn't lead to significant issues.
This is all great for request-based APIs, but what about systems that use WebSockets? You have a persistent connection, so the traditional rate-limiting algorithms don't seem to apply directly.
That's a fantastic point. WebSockets introduce a whole new layer of complexity. You can't simply count individual requests. You need to consider the bandwidth being consumed by each connection. Think of a real-time chat application. You don't want one user to flood the server with messages, degrading the experience for everyone else.
So, how do you rate limit bandwidth on a WebSocket connection?
One approach is to track the number of bytes sent or received per connection over a sliding window. If a connection exceeds the bandwidth limit, you can temporarily throttle the connection or even disconnect it. Meta probably uses techniques like this to manage the load on their Messenger and WhatsApp WebSocket servers.
That makes sense. It's about adapting the rate-limiting strategy to the specific communication protocol and the resources being consumed.
Exactly. And here's where it gets interesting. Most engineers focus on the technical implementation of rate limiting, but they often overlook the business context.
What do you mean by business context?
Think about it. Should a paying customer be subject to the same rate limits as a free user? Should a critical API endpoint have a higher rate limit than a less important one? The answer is almost always no. You need to tailor your rate limiting strategy to the specific business requirements.
So it's not just about preventing abuse, it's about optimizing the user experience and maximizing revenue.
Precisely. Imagine SaaS companies like Stripe. They might offer different rate limits to different customers based on their subscription plan. High-paying customers get higher limits, while free users get lower limits. This incentivizes users to upgrade to higher plans and generates more revenue for the company. It's a win-win.
Okay, I see your point. It's about aligning the technical implementation with the business goals. What's one thing software engineers can do today to improve their rate-limiting strategy?
First, understand your traffic patterns. Don't just guess at the appropriate rate limits. Use monitoring tools to analyze your API traffic and identify potential bottlenecks. Second, implement adaptive rate limiting. Don't use static rate limits. Dynamically adjust the limits based on the current load and the available resources. Think of it like cruise control for your API.
Adaptive rate limiting sounds complex.
It can be, but it's worth the effort. And third, communicate clearly with your users. Provide informative error messages when users are throttled. Tell them why they're being throttled and when they can retry. Don't just leave them guessing. Think of it like giving drivers a detour map instead of just a road closed sign.
So understand your traffic, adapt dynamically, and communicate clearly. Those are 3 actionable steps.
Exactly. Remember, rate limiting isn't just about preventing abuse. It's about ensuring a fair and sustainable ecosystem for your APIs. It's about building a resilient system that can withstand the inevitable storms.
I like that. It's not just a dam, it's about building a seawall for your entire API.